Hello there, and welcome to Science for Sleep, where curiosity takes the long way around, and even the coldest questions are softened until they feel calm enough to wander through. Tonight, we're going to step into a place so extreme it almost sounds impossible. It's not just cold, it's the very bottom of cold, the point where heat runs out of places to go. The place physicists call absolute zero. Now that's a term you might have heard before, maybe in a movie or tucked away in an old science textbook. But what it really means is stranger than it sounds, because at that point the very motion of atoms slows until it nearly stops. Time itself seems to stretch thin, and the familiar rules of our warm everyday world begin to slip away. But before we sink down toward that frozen edge, I'd like to ask you something simple. Where are you listening from right now? Maybe you're curled up under a blanket with the glow of a screen painting soft shadows on the walls. Or maybe you're lying there in the quiet, letting your thoughts settle like snow. Either way, if you'd like this to be a place where you can let the day fade out while still learning something quietly fascinating, I'd be grateful if you'd give this video a like, or even subscribe. It helps this little corner of calm reach more night thinkers who might also want to drift through strange ideas while they rest. Now, let's take it slow, because absolute zero isn't just a temperature, it's an idea. And ideas like this have a way of changing how you look at the ordinary world around you. When you touch a warm mug of tea or feel the cold air from an open window, what you're really sensing isn't some invisible quality called hot or cold. You're feeling motion. Heat is motion. Every particle, every atom, every molecule in your body and in the air around you is always jiggling and bouncing around. When it's warmer, they jiggle faster, and when it's colder, they slow down. It's a dance so small and constant that we never see it, but it's there, every second. Now, imagine turning that motion down further and further, like lowering the volume on a song until it's almost silent. If you keep going, in theory, there comes a point where that motion nearly stops, and that's absolute zero, negative 273.15 degrees Celsius, or 459.67 degrees below 0 Fahrenheit. Numbers so low they feel less like temperature and more like an argument with reality. It's colder than the coldest places in deep space, colder than anything you'll ever feel on Earth. In fact, it's so cold that it can never truly be reached, because as you try to get there, the universe keeps pulling it out of reach like a mirage. But even if we can't quite touch it, scientists have learned how to creep closer and closer to it. And the closer we get, the stranger things become. Atoms start behaving less like little balls of matter, and more like ripples in a single invisible pond. Whole clouds of particles merge into what's called a Bose-Einstein condensate, a kind of ghostly state of matter where the line between one atom and the next almost disappears, and what's left is something that moves as if it were one single thing. It's not just cold, it's a new way of existing. And it changes how we understand the universe itself, because at absolute zero, our familiar rules start to fade away and quantum rules take over, the kind that don't care about our ordinary sense of time, or common sense, or even logic. The kind that make you realize that this temperature, at the very bottom of possibility, isn't just a number on a scale, it's a doorway to the hidden machinery of reality. But before we plunge all the way down, let's pause for a moment and think about what temperature really is. Because if you've ever wondered why we even talk about zero in the first place, why there's a bottom to the scale at all, it helps to go back to a world before thermometers, before scientific laws, when heat was just something people felt in their bones. Fire warmed the skin, ice bit through it, and no one imagined that these sensations were tied to the frantic dance of invisible particles. It wasn't until we learned to measure heat, not just feel it, that the true scale of it began to appear, and buried at the very end of that scale, in the deepest cold imaginable, was a boundary that no one could cross but everyone wanted to understand. This boundary, absolute zero, isn't just a temperature. It's the closest thing physics has to silence. And in that silence, particles lose their individuality. The randomness that fills our everyday world calms down, and order begins to creep in. In a way, it's almost unsettling, because when motion slows that much, even the concept of time starts to shift. Time is measured by change, and at absolute zero, there's almost nothing left to change. And yet, it's in that strange, almost frozen stillness that nature hides some of its deepest secrets, superfluids that can flow without friction, exotic quantum states that defy intuition, and matter behaving in ways that feel more like thought experiments than real things you can trap in a lab. This is why scientists build machines colder than the vacuum of space, not because they want to freeze something for the sake of it, but because in that deep, quiet cold, the universe shows a side of itself that simply doesn't exist anywhere else. The funny thing is that while this temperature sounds impossibly remote, pieces of it touch your life every day. The microchips inside your phone and computer depend on quantum behaviours that were first glimpsed in the shadow of absolute zero. The precision of atomic clocks, the ones that keep GPS satellites in sync and let you find your way home, rely on an understanding of matter that came from studying what happens when the universe's heat almost vanishes. Even some of the most futuristic ideas in physics, from quantum computers to theories about the beginning and end of the cosmos, are shaped by what we've learned from those experiments that stare straight into the abyss of cold. And as strange as it might sound, the closer we look at this impossible temperature, the more it begins to feel less like an endpoint and more like a mirror. Because at absolute zero, you're not just looking at cold, you're looking at the limits of what motion means, what energy means, and maybe even what reality itself means. So let's keep drifting downward, gently, 1 degree at a time. Because the world at absolute zero is not empty. It's full of quiet revelations, waiting in the deep stillness where the ordinary rules loosen their grip and something new begins to emerge. If absolute zero is the bottom of the scale, then this is the part of the story where the scale itself starts to feel unreal. The very phrase absolute zero almost sounds like it was invented as a dare, a number so extreme it hovers at the edge of meaning. Negative 273.15 degrees Celsius, not a fraction warmer, not even the faintest flicker of heat left in it. And yet, it isn't simply cold. It's the place where cold, as we know it, stops working. The strange, unreachable border where temperature ceases to be a thing we can fully imagine. For most of our lives, temperature is simple. We live in a world of warm blankets and cool breezes, of hot coffee and cold hands on winter mornings. Numbers we can understand. 40 degrees feels sweltering, 0 feels icy, and we think we've seen the whole scale. But the truth is that our everyday experience barely skims the surface of what temperature actually means. Because temperature isn't a sensation, it's motion, a way of measuring how much the tiny building blocks of matter are jostling against each other like an endless, invisible crowd. When things get hotter, those particles bounce harder, collide faster, and spin with more energy. And when they get colder, they slow down. But here's where it turns strange, that slowing has no natural stopping point. There's no lowest rung, no final floor you can land on. Instead, each step downward costs more energy to take than the one before it, until you reach a place where every fraction of a degree is a monumental effort. And that is where you meet the concept of absolute zero. The idea came from the slow, steady march of science centuries ago, when we first began to understand that heat wasn't a substance you could pour or store like water, but something tied to motion itself. People like Lord Kelvin, who gave us the very scale that bears his name, realised that if heat is motion, then there must be a point where motion ends, and if motion ends, then temperature ends too. That number became 0 on the Kelvin scale, not just as a convenience, but as a boundary drawn by nature itself. But here's the part that feels almost mischievous. While this number has a name and a neat place in textbooks, the universe refuses to let us touch it. No matter how clever our machines become, no matter how many lasers or magnetic traps we build, we will never truly arrive there. The third law of thermodynamics stands in the way like an unmovable signpost. The closer you get to absolute zero, the harder it becomes to keep cooling. The last scraps of motion cling stubbornly to matter, like whispers you can't quite quiet completely. And yet, even though we can't reach it, that hasn't stopped us from chasing it, piece by piece, degree by degree. And every time we push a little closer, the world beneath those temperatures becomes stranger. What was once solid and ordinary begins to behave in ways that look like they belong in science fiction. Gases collapse into a single, unified state, where every particle shares the same quantum identity. Metals lose all electrical resistance and become perfect conductors. Fluids learn how to flow forever without slowing down, as if friction simply gave up and walked away. But this isn't just a laboratory curiosity. The fact that absolute zero exists as a concept changes the way we see the universe itself. It tells us there's a flaw beneath all the restless energy we live with. A kind of cosmic silence that everything leans toward but never quite reaches. And it raises a question that's far more unsettling than it first appears. If the universe has a temperature it can never reach, what does that say about its limits? Or about whether time itself would mean anything if it did? Because if you think about it, temperature is tied to time in a way we don't often notice. The hotter something is, the more its particles move, the more collisions there are, and the more events happen per second. Now imagine dragging everything down to absolute zero, where motion halts entirely and collisions stop. What would time look like then? Would it still make sense to talk about seconds passing if nothing is changing in those seconds? These are not just thought experiments for the late hours. Scientists have built machines to creep down to billionths of a degree above that unreachable zero, not because they expect to beat the laws of nature, but because they want to see what happens when the familiar scaffolding of our world falls away, and every single rule we take for granted has to be rewritten in the language of quantum mechanics. And in those labs, they've seen things that look like the universe itself turning inside out. But even as we chase that number, even as we come closer to the edge of this impossible temperature, absolute zero remains more like an idea than a destination. It's the ultimate boundary, the place that gives shape to the scale above it. Without it, our concept of temperature wouldn't have an anchor. It's not just a cold point, it's the reference that every degree of warmth is measured against. And that means that, in a strange way, this temperature that shouldn't exist is the one that holds all the others in place. And so, we keep moving downward, following it step by step like a distant horizon that never stops retreating. Every new experiment brings us a little closer, but not close enough to erase the gap. And in that gap is where the most interesting things hide. Because if absolute zero were just another temperature we could reach and tick off a list, it would lose the mystery that makes it worth chasing. Instead, it stays out there, untouchable, setting the stage for everything we're about to see as we keep descending. And as we do, it's going to get even stranger. Because while absolute zero might be an impossible destination, the road toward it is full of stops where the ordinary world fades away and the rules change into something unrecognizable. The closer we get, the more the world begins to feel unfamiliar. Not because the numbers on the thermometer are dropping, but because every step downward is like peeling back a layer of reality that we didn't know was there. This is where temperature stops feeling like something you could touch or sense, and starts feeling like an idea. A countdown into a place where all the busy, restless energy we take for granted slowly fades into silence. Think about what happens when you cool something down in the ordinary world. You can feel it shrink in on itself. Liquids thicken, metals become rigid and brittle, air feels heavier. But underneath all of that, what's really happening is motion losing its strength. Every atom, every molecule that makes up that thing is slowing down. Not stopping yet, but edging closer to a kind of stillness that's hard to imagine. because stillness isn't really something we've ever experienced. The room you're in right now is full of motion, even if it looks perfectly still. The air around you is full of vibrating molecules. Your body is alive with chemical reactions. Your atoms are buzzing quietly with the restless hum of heat. But as you count down toward absolute zero, that hum dims. It's not a sudden change. It's a gradual surrender, one fraction of a degree at a time. And with each step, the rules start to bend. Atoms stop behaving like little individual marbles bouncing around and start blending into one another. The closer you get, the less they act like separate objects, and the more they move together, as if the whole world were slipping into one single collective rhythm. This isn't just a metaphor. In the deep cold of that descent, particles really do begin to lose their individuality, their quantum states overlapping until they become almost indistinguishable. This is why scientists sometimes describe this process not as cooling, but as watching matter collapse into unity. And it's not just the atoms that change, it's the very way we measure what's happening at these temperatures. Because at room temperature, or even the coldest winter you've ever stood in, the way we think about heat still belongs to the classical world, the world of thermometers and simple cause and effect. But near absolute zero, that thinking breaks apart. The ordinary math doesn't work anymore, and what replaces it is a view of the universe that has been hiding in plain sight all along, the quantum world. Down here, even the idea of temperature starts to lose its meaning. Because temperature depends on motion, and motion depends on energy. And energy in this place comes in discrete packets. Not the smooth, continuous flow we're used to. It's like walking down a staircase that's been crumbling away beneath your feet. Each step takes you lower, but the steps are no longer even. They're quantized. Strange, sudden drops separated by spaces where nothing seems to happen until suddenly, something does. This is why cooling something from 10 degrees to 1 degree feels easy. But cooling it from 1 degree to 1,000th of a degree is like dragging the universe uphill with your bare hands. Every bit of energy you remove gets harder to pull away because there's less of it left to take. Each scrap of heat is locked tighter than the last, and every step down costs exponentially more work. It's as if nature built a hidden resistance into the bottom of the scale, a kind of quiet defense against ever reaching that final zero. But that's also what makes this descent so fascinating, because the closer you get, the stranger it gets, and you start to see hints of things that don't exist anywhere else in the universe, not in stars, not in planets, not in anything we'd call ordinary. This is where superfluid helium can climb up the walls of its container, as if gravity doesn't matter. This is where atoms, that should be bouncing around like a room full of unruly children, suddenly settle down and march in perfect lockstep as if some invisible conductor raised a baton. This is where electrons stop wasting energy and flow without resistance, forever, in a loop that never fades. And every one of these steps downward is a reminder that this isn't just a number. This isn't just another scale of temperature. This is what happens when you strip the universe down to its barest possible state. When you keep peeling away motion until almost nothing is left, except the rules that have been buried underneath everything else from the beginning. But here's the strangest part. The closer you move toward that ultimate nothingness, the more you realize there's something there. It isn't empty. It's full of hidden order, full of laws that only reveal themselves when everything else has gone quiet. It's a kind of paradox. Absolute zero sounds like the end, but it behaves like a beginning. And that's what keeps scientists chasing it, because every step down isn't just about colder temperatures, it's about peeling away one more layer of what we think is normal to find out what's been sitting underneath all along, and if we keep counting down, we'll find even more waiting for us. Because what happens next is the point where motion doesn't just slow, it practically vanishes, and matter starts to act in ways that seem impossible anywhere else. This is where heat stops being just something you can feel and turns into something you can almost watch unravel if you know how to look. Because when you reach the edge of the thermometer and keep going further and further toward absolute zero, something extraordinary happens. atoms stop behaving the way we think atoms should behave. At the temperatures you and I know, even the coldest winter night or the most carefully cooled freezer, the atoms around you are still buzzing. They vibrate, they jostle, they crash against each other in a quiet, endless chaos that never really stops. And that constant dance of motion is what keeps the world we know alive and moving. But as you push toward absolute zero, the dance slows. It doesn't just slow a little. It slows so much that the steps between one movement and the next stretch out almost endlessly until the jostling nearly disappears entirely. In this frozen world, an atom doesn't shake the way it used to. Instead, it sinks down toward its lowest possible energy state, the point where there's nowhere left to go. And that's where something strange happens, because at that moment, the rules we're used to stop applying. It's not just that the atom is still, it's that stillness itself becomes an entirely new kind of motion, one defined not by the ordinary world, but by the quantum world, the world that lives underneath everything else. You see, at these unimaginably low temperatures, atoms stop acting like tiny billiard balls and start acting like waves. Not waves of water, but waves of probability, spreading out until they overlap with the waves of other atoms in the same space. This is what gives rise to something called a Bose-Einstein condensate, a state of matter so alien to our ordinary lives that it barely seems real. In this state, thousands or even millions of atoms stop behaving as individuals entirely and begin to move as one unified entity. It's as if all of them have agreed to share a single identity, a single quantum state. Imagine a crowd so perfectly synchronized that no one in it makes a move on their own. Instead, they all shift in flawless unison, each step, each motion perfectly aligned. That's what matter begins to do when it's pushed this close to absolute zero. Individuality disappears, and the entire system behaves like a single, enormous particle. And it's not just a neat trick, it's a glimpse at what reality looks like when all the usual noise has been drained out of it, when the universe is quiet enough to show us what's underneath. But the stillness isn't perfect, because there's something built into the heart of quantum mechanics called zero-point energy. And that means no matter how cold you make something, no matter how far down you push it, atoms can never quite stop moving completely. They always retain a faint shimmer of energy, a tiny, irreducible vibration that refuses to vanish. It's as if the universe has written a rule that says nothing can ever be perfectly still. Not entirely, not even for a moment. And it's this rule that saves absolute zero from being more than just a number, because it turns it into a horizon you can approach but never cross. A place that's defined as much by what you can't do as by what you can. This is why scientists keep building colder and colder machines. Not because they think they can reach zero itself, but because every step closer lets them see what matter is hiding in this strange boundary land between motion and stillness. And what they find there changes everything. Take superfluids, for example, substances that, when cooled almost to zero, lose all viscosity entirely. Pour them into a container, and they'll creep up the walls like they're defying gravity. Not because they're alive or magical, but because the ordinary friction that should slow them down has simply stopped existing. Or superconductors, metals chilled so far down that electrical resistance vanishes. Electrons flow forever in a loop without losing a single scrap of energy, as if the concept of waste itself has been erased. These things sound impossible, but they happen right here in our world, and only because we've learned how to walk atoms almost to the brink of stillness and watch what they do. And the closer we look, the clearer it becomes that absolute zero isn't really an endpoint. It's a place where a different version of reality waits quietly, just out of reach. And in that frozen quiet, even time begins to feel different. Because if motion slows this much, if collisions nearly stop and atoms merge into a single shared existence, what does it even mean to talk about 1 second passing after another? How do you measure time when almost nothing is changing? It's a question that physicists don't answer so much as circle around, because every time we look closer, another layer of this strange, quiet world peels away and shows us something new. And if this is what happens when motion freezes, then what happens next might be even stranger. Because at these temperatures, it's not just the atoms that begin to change, it's the very fabric of what we think energy is. And the deeper we go, the more it starts to feel like we're not just studying cold anymore, we're studying the foundations of everything. The deeper we descend, the closer we come to the point where heat itself loses every foothold it has, the kind of place where warmth isn't just rare, it's impossible. Where energy, this restless, invisible currency that drives everything we know, runs out of moves to make until there's nothing left but stillness. To understand why this happens, we need to remember what heat really is. Because for most of us, heat feels like something simple. You touch a mug of coffee and it's hot. You step outside on a winter night and it's cold. But beneath those feelings, heat is nothing more than motion. It's atoms jiggling, vibrating, colliding against one another in a constant shuffle of energy. Every bump and every tiny exchange creates the sensation we call temperature. But as we keep pushing down the scale, stripping away the energy from that motion, we begin to reach a strange frontier. Every degree we remove takes us closer to the point where there is no extra motion left to drain. The particles don't just slow, they collapse into their lowest possible state of energy, the state they can't sink beneath. And at that point, heat, the very thing we've been cooling away, simply ceases to exist. And this is where the third law of thermodynamics steps in like an unbreakable barrier. It says that as you approach absolute zero, the amount of energy required to remove those last scraps of motion grows infinitely large. In other words, nature doesn't let you hit zero. The cost of extracting that final flicker of movement becomes impossible. It's not a matter of better technology or more powerful machines. It's a fundamental rule of the universe. But even though we can't reach it, every step closer reveals something astonishing. Because when energy drains out of a system and motion fades, what's left isn't nothing, it's order. The wild randomness of particles crashing into one another starts to settle, and in that deep quiet, new behaviours emerge. Behaviours that only exist when the usual chaos has been frozen away. One of the most striking examples of this is in those exotic states of matter that appear near absolute zero. Superfluids and Bose-Einstein condensates we talked about before, these are not just scientific curiosities, they're demonstrations of what happens when heat loses its grip entirely, when energy has been drained so thoroughly that the only thing left guiding matter is the subtle, precise machinery of quantum physics. In this place, friction disappears, electricity flows without resistance, particles behave less like individuals and more like pieces of a single, continuous wave. And all of it comes from the simple fact that there's no thermal energy left to shake them out of this strange unified order, but there's something even deeper hiding in this idea. If heat is motion, and motion is change, then what happens to time in a place where motion is gone? At the edge of absolute zero, when energy is reduced to the faintest whisper, and atoms have been pressed into perfect stillness, time begins to look less like something that moves forward and more like something that simply is, a frozen landscape rather than a flowing river. Now, of course, we never quite get there. The zero-point energy built into the quantum world prevents anything from being perfectly still. There's always a faint hum in the background, a reminder that even at the edge of nothingness, the universe refuses to be completely silent. But that hum isn't the same as the noisy motion we know at ordinary temperatures. It's the faint residue of existence itself, the smallest possible flicker of energy written into the fabric of reality. And this is what makes the end of heat so fascinating, because it isn't the end of matter or the end of physics. It's the place where our familiar picture of the world gives way to something hidden, a set of rules that only appear when energy has been stripped down to almost nothing. This is why scientists build their extraordinary cooling machines, lowering atoms to billionths of a degree above zero, not because they want to see how cold something can get, but because every fraction of a degree peeled away brings them closer to this quiet world, where the ordinary dissolves and the quantum takes over. And in that quiet, they can watch the universe behave in ways that look more like thought experiments than physical reality. And yet, for all of its strangeness, this end of heat isn't just an abstract concept. It shapes things in the world you live in. The chips inside your phone rely on principles first discovered in these extreme conditions. Quantum mechanics, superconductivity, and the technology of tomorrow all trace their roots back to this frozen edge of physics, where heat finally runs out of places to hide. And if this is what happens when energy fades to almost nothing, then the next step downward might be even stranger. Because what lies just below this boundary isn't just about temperature or motion anymore. It's about the fabric of existence itself. Now we're moving into a place where the ordinary rules of the world fade away and something stranger begins to speak. When heat drains out, when motion nearly vanishes, and when atoms settle into that eerie stillness near absolute zero, the quantum world stops hiding in the background. It steps forward, quietly, relentlessly. And what it shows us doesn't feel like the world we know. It feels like something that was always there, waiting beneath the noise of temperature and motion, as if the universe itself has been whispering all along, but only in the kind of silence you find at the bottom of the cold. In our everyday lives, we don't notice quantum mechanics. It's not that it isn't there. It's just drowned out by everything else. By heat, by collisions, by the sheer chaos of trillions upon trillions of particles smashing around at once. That chaos hides the subtler rules, the ones that govern things on the smallest scales. But as we approach absolute zero, the noise fades, the collisions slow, the clutter of motion falls away, and for the first time the whispers underneath can be heard. And those whispers are strange. They tell us that particles are not really solid, not really separate, and not really where you think they are. They exist in overlapping clouds of probability, and when you remove almost all of their thermal energy, those clouds expand and begin to overlap until the distinction between this atom and that atom starts to blur. Instead of many things, you begin to see one thing. This is the world of quantum coherence, and it is most clearly revealed in that deep frozen dark. Here, atoms don't just share space, they share identity. When you cool a cloud of atoms to within a billionth of a degree of absolute zero, they collapse into a Bose-Einstein condensate, a single, unified quantum state. It's not a metaphor, it's a literal transformation. Those countless individual atoms move together as though they are one. They stop behaving like independent particles, and instead act like one enormous wave stretching across the entire system. You can't point at one part and say, this is where one atom ends and the next begins, because there's no such boundary anymore. In this frozen darkness, quantum rules no longer compete with temperature, they dominate. And when they dominate, the world looks alien. Superfluids flow without resistance, ignoring the normal rules of friction. Superconductors carry electrical currents forever, without a single bit of energy leaking away. And quantum tunneling, the phenomenon where particles slip through barriers that should be impossible to cross, becomes not just an occasional quirk, but an ever-present part of reality. This is why scientists build their elaborate cold traps and magnetic fields. Not because they want to conquer cold itself, but because they want to hear these whispers more clearly. They want to strip the world down until only the fundamental rules remain. And in that frozen silence, they find that the universe is not mechanical in the way we were taught to think. It's fluid, probabilistic, interconnected. And in that interconnectedness, particles do things that defy ordinary logic. What's even stranger is how this frozen quantum world touches our everyday lives, even if we never see it. The processors inside your computer, The sensors in your phone, the lasers used in medicine, all of them exist because we've learned how to listen to those whispers. Without absolute zero, or at least the journey toward it, we would never have learned how to bend quantum mechanics into something we can use. But it's not just technology that hides here. There's something deeper, something philosophical in the way the quantum world emerges from the cold. Because if you think about it, what we're really watching in these experiments isn't just matter changing state. We're watching reality itself change its behavior. We're seeing what happens when the universe's most hidden rules are allowed to speak without interruption. And the deeper we go, the quieter it gets. Not quieter in the sense of silence you can hear with your ears, but quieter in a way that feels almost unnerving. Because this is the silence where nothing moves unnecessarily, where nothing happens by accident, where every remaining trace of energy is dictated not by chaos but by structure. The world becomes simpler, sharper, almost unnaturally perfect, and yet it's not truly still. 0-point energy remains, that faint, unavoidable hum of motion that even the universe can't erase. That hum is important. It's a reminder that there is no absolute emptiness. Even in this frozen dark, the universe never fully stops. Instead, it balances on the edge of motion and stillness, a kind of suspended state where everything you thought was separate begins to feel connected. And the more you stare at it, the more it begins to feel like absolute zero isn't just about temperature at all. It's about stripping the world down to its rawest form. And if this is what the whispers sound like here, in this place just above absolute zero, then the question becomes, what else is waiting in this frozen world just out of reach? Because we're not done descending. Not yet. There's still more hidden beneath this quiet, and if we keep going, we might just see how even entropy itself starts to rest. This is where the descent stops feeling theoretical and starts becoming something you can almost see. At these temperatures just a breath above absolute zero, matter itself changes into something so strange, so quiet, and so unlike anything we know that it hardly feels real. This is the home of Bose-Einstein condensates, where particles stop being separate things and begin to merge into a single ghostly state. Under normal conditions, every atom is its own little world. It spins, it vibrates, it moves through space, and it keeps to itself. Even when you pack them tightly into a solid block of matter, each atom is still an individual, jostling and bouncing in its own way. Heat fuels this individuality. The constant motion scrambles them and keeps them apart. But near absolute zero, the heat that once defined their independence is stripped away. Motion slows, energy drains, and what's left behind is not just colder, it's simpler. When matter reaches this edge of cold quantum mechanics, the deep, invisible set of rules that normally hides underneath the noise of the everyday world starts to take over. And when it does, atoms stop behaving like individual particles. They spread out, they blur into waves. Those waves overlap and begin to lock into place. It's no longer a million separate things. It's one. A Bose-Einstein condensate. This state of matter is unlike any other. Imagine a room full of people, all talking, all moving, all thinking their own thoughts. That's matter at ordinary temperatures. Now imagine that somehow every single person in that room stops moving, stops speaking, and begins to act with one perfect shared purpose. Not because they've been ordered to, but because the very rules of existence demand it. That's what happens inside a Bose-Einstein condensate. Millions of atoms merge into a single quantum identity. They move as one. They exist as one. You can't tell where one atom ends and another begins because in a very real way, they've stopped being separate things at all. When this was first predicted, it sounded impossible. In 1924, Satyendra Nath Bose and Albert Einstein imagined what would happen if matter were cooled so far that quantum effects could no longer be ignored. They theorized that if you removed enough heat, particles would collapse into the same lowest energy state. but at the time there was no way to reach such a temperature. It wasn't until 1995 that scientists finally created the first Bose-Einstein condensate in a laboratory by cooling a cloud of rubidium atoms to just a few billionths of a degree above absolute zero. And when they looked at what they had made, it was exactly what Bose and Einstein had described: an entirely new state of matter, one that moved like a single, unified ghost. And the word ghostly isn't an exaggeration. When you peer into a Bose-Einstein condensate, you don't see a collection of separate particles anymore. You see a single smooth entity, a shimmering cloud where every atom is synchronized. It's as if matter has stopped arguing with itself and decided for once to act like one thing. But the strangeness doesn't stop there. In this ghostly state, matter can do things that sound impossible in the ordinary world. A Bose-Einstein condensate can flow without friction. It can interfere with itself like a wave of light. It can even exist in overlapping states, where the difference between here and there starts to lose its meaning. This is not the kind of matter that builds walls and coffee mugs and car engines. This is matter stripped down to its most fundamental, most unreal behaviour, a glimpse of what the universe is made of when it's quiet enough to listen. And yet, even though this sounds abstract, this ghostly state is not just a curiosity locked in a laboratory. It is a key to understanding the deepest rules of reality. When scientists study Bose-Einstein condensates, they are not simply learning about cold atoms. They are learning how quantum mechanics works on a scale large enough to see, how particles interact when individuality disappears, and even how the early universe might have behaved in its first moments, when everything was packed into a single, uniform state. Because in a strange way, a Bose-Einstein condensate is a kind of echo of the beginning. When you cool matter this far down, you're forcing it into a state of almost perfect order. A state that might resemble what the universe looked like before motion, before heat, before complexity. It's as if by chasing absolute zero, we're not just exploring the edges of temperature, but brushing against the edge of time itself. And that is why this ghostly state matters. It's not just science for its own sake. It's a reminder that buried beneath the familiar world of warmth and movement is a quieter, stranger universe that only reveals itself when everything else has been stripped away. But we're not done yet. Because if Bose-Einstein condensates show us what happens when matter unites, the next step downward will show us what happens when even entropy, the great engine of disorder, finally begins to rest. This is where the silence of the cold deepens into something even stranger. We've seen how atoms slow, how matter merges into a single ghostly state, and how the familiar world begins to dissolve into something quieter and more unified. But if we keep going, if we imagine ourselves moving even closer to absolute zero, we come face to face with a concept that has always been tied to the arrow of time itself: entropy. And here, at the edge of the frozen dark, we begin to see what it looks like when entropy almost stops. Entropy is usually the great unstoppable tide of the universe. It's the tendency for things to drift from order to disorder, for neatness to unravel, for heat to spread out until everything is evenly dull and quiet. It's why a drop of ink disperses in water and never gathers itself back again. It's why broken cups don't leap off the floor and reassemble themselves. And it's why time, as we experience it, always seems to move in one direction. Entropy grows, disorder spreads, and we move forward with it. But near absolute zero, entropy is brought to heel. When you cool a system to the edge of this unreachable temperature, something happens that doesn't occur anywhere else in nature. The random motion that fuels disorder fades. The collisions that scramble energy and scatter it into every corner of the universe nearly vanish. Instead, everything locks into place. Atoms lined up in their lowest energy states with no room left to fall any further. The chaotic shuffling of heat is replaced by an eerie stillness where there are no more moves left to make. This is why scientists sometimes describe absolute zero as the point where entropy reaches its minimum. It's not zero, not quite, because quantum mechanics won't allow it. That faint hum of zero-point energy is still there, the tiny, irreducible vibration of a universe that can never fully stop. But compared to the restless storm of ordinary matter, it's almost nothing. It's as if all the disorder has been drained away, leaving only a quiet, perfectly arranged structure, matter as close to absolute order as the laws of physics will ever allow. And here's the astonishing part. This isn't just theoretical. In the laboratory, when scientists cool materials to billionths of a degree above absolute zero, they can watch entropy's grip loosen. They see particles falling into alignment, energy levels narrowing until everything behaves as if the universe itself has taken a deep, steady breath. A cloud of atoms, once a mess of random motion, collapses into a Bose-Einstein condensate. One unified wave. Superconductors switch on and begin conducting electricity with flawless efficiency. Superfluid starts sliding without friction. Forever. These are not just experiments. They are glimpses of a world where entropy no longer dominates, where the universe, at least in this tiny frozen corner, stops flowing in its usual direction. But what's even more unsettling is what this implies for time itself. If entropy is tied to the arrow of time, if the increase of disorder is what gives us a sense of past and future, what does it mean to reach a place where entropy has nowhere left to climb? In this deep frozen stillness, time feels less like a current and more like a frozen lake. Events stop tumbling over one another, they simply hold. It's not that time disappears, but its movement loses the urgency we're used to. In this strange world near absolute zero, the universe looks less like it's rushing forward and more like it's paused, hovering on the edge of motion and change. Yet even in this pause, the faint hum of quantum mechanics remains, and that hum matters. Because if entropy could truly reach zero, if disorder could be erased completely, everything would be locked forever, with no possibility of change. The universe would become a perfect crystal of stillness. But that never happens. There is always that whisper of energy, that trace of motion, that reminder that nothing in this universe can be perfectly frozen. And maybe that's what keeps the story going, because without that faint hum, there would be no time, no change, no future, nothing at all. So, entropy never truly dies. It only slows. It waits in this deep quiet, reduced to its barest form, like a candle's last ember glowing in an endless night. And in that stillness we see what the universe is built on, a balance between the relentless pull of disorder and the silent boundary that holds it back. But as strange as this frozen calm is, it's not the end of the descent, because even here, at the edge of entropy's rest, there are deeper questions. What happens to time itself when the universe is this still? What does it mean for energy, for matter, for reality, when everything sits this close to the edge of nothing? If anything has been hiding quietly behind all of this, beneath the slowing atoms, beneath the vanishing heat, beneath entropy itself, it's time. We live our entire lives inside its current. It pushes us forward whether we want it to or not. It shapes our days, measures our years, and gives our world a before and after. But down here, near the bottom of the thermometer, time doesn't feel the same. It doesn't flow the way it does in the world of warmth and motion. It hangs differently, stretched and quiet, like something that's been muted almost to silence. Time, as we usually think of it, depends on change. We mark it by things happening, by clocks ticking, by the earth turning, by particles colliding and exchanging energy. But at temperatures near absolute zero, change slows almost to a halt. The atoms that once danced furiously are reduced to their lowest energy states, their motion so faint it's barely there at all. If you could stand here, not in a real sense, but in the way the mind imagines. You would find yourself in a kind of suspended world, one where the usual rhythm of events has been thinned to its barest thread. And that raises a strange question. If almost nothing moves, does time still matter? Or does it just sit here too, waiting for something, anything to happen? Physics has an answer, though it's not the one that makes you comfortable. Time doesn't disappear, but it becomes abstract. At these temperatures, what we call time is no longer a steady tick-tock for every observer everywhere. Instead, it becomes tangled with energy, with motion, with quantum rules that stretch and bend the way we usually understand it. Near absolute zero, the line between then and now grows thin. Events stop piling on top of one another in the usual way. It's as if time, at least here, has less to do. Quantum mechanics makes this even stranger. Down here, where particles overlap and form single unified states, the usual notion of cause and effect starts to blur. When millions of atoms merge into a Bose-Einstein condensate, they stop acting like individual things moving through time one by one. Instead, they behave like a single quantum wave, existing all at once in one vast shared state. In that wave, time isn't something you measure from particle to particle. It's something that stretches across the whole system at once, as though the usual clock we use to count it has been replaced by something slower, softer, less local. And this isn't just theory. Experiments have shown that near absolute zero, certain processes that normally tick away with perfect regularity can stall. Chemical reactions that would happen in a blink at room temperature crawl almost to nothing. Even quantum fluctuations, the jittering, unpredictable background activity of the universe, quiet down until they're barely detectable. It's not that time has vanished, it's that it's been emptied of its usual urgency, leaving only a long, frozen moment where almost nothing happens at all. But here's where it becomes even more unsettling. If time slows this much for matter in this frozen state, what does that say about the deep connection between time and heat itself? If the arrow of time is tied to entropy, the tendency of the universe to spread out and unravel, what happens in a place where entropy has been brought to a near stop? Some physicists have speculated that in these frozen conditions, time might not be something that flows independently at all. Instead, it might simply be a measure of change, and when change almost disappears, time does too. This doesn't mean that time dies at absolute zero. Even here, 0-point energy, the faint, unkillable hum of quantum motion, remains. And that hum carries with it just enough activity to keep the universe from locking into perfect stillness. In a way, that leftover motion is what keeps time alive, even here in the deep freeze. Without it, there would be no difference between one moment and the next, no reason to say that anything happens at all. And maybe that's the most fascinating thing about this frozen edge of existence. It doesn't erase time, it exposes it. It shows us that time is not a universal stage running in the background. It's a property that depends on motion, energy, and change. Strip those things away and time thins out like air at the top of a mountain until only the barest trace of it remains. If this is what happens to time near absolute zero, then what we're about to see next goes even further. Because now we reach the question that scientists have been chasing since the beginning. Can absolute zero itself ever truly be reached? Or is it a horizon that will always retreat no matter how far we go? We've been sliding further and further down the thermometer, peeling away motion, draining heat, and quieting the restless chaos of matter. And now, we've arrived at the edge of the coldest idea there is. Absolute zero. A temperature so low it feels less like a number and more like a wall in the fabric of reality. But here's the thing, can we ever actually reach it? For centuries, the idea of absolute zero has tempted physicists, almost like a dare written into nature itself. The number is clear, minus 273.15 degrees Celsius, 0 Kelvin, the end of heat. But if you try to get there, you discover something strange. the closer you move toward it, the more it pushes back. It's as though the universe has hidden it behind an infinite series of locked doors. The reason is rooted in one of the most unyielding laws of physics, the third law of thermodynamics. This law says that as you approach absolute zero, the amount of energy you need to remove in order to cool something further increases without limit. Each fraction of a degree costs more than the last. At first, cooling is simple. Take a warm object and it gives up its heat easily, but as you move down, that heat becomes harder to extract. The particles cling to their last traces of motion, and stripping away that final sliver of energy becomes an impossible task. It's like chasing a horizon. You can keep getting closer and closer, but you never quite touch it. You can slow atoms until they are moving so faintly that their behaviour almost stops resembling anything familiar. You can cool a system to billionths of a degree above zero. But the last step, the one that would take you all the way, is forever out of reach. And even if you could somehow take that step, quantum mechanics would stop you. Because down here, near the bottom of the scale, 0-point energy begins to matter. It's the faint, unkillable hum of the universe, the lowest level of energy that even the coldest object cannot lose. No matter how hard you try, you can't erase it. It's built into the very fabric of reality. Even if everything else went still, that subtle vibration would remain, keeping the universe from ever truly freezing. But that doesn't mean our journey down the scale is pointless. Far from it. Even if absolute zero itself is unreachable, the pursuit of it has led us to some of the most astonishing discoveries in physics. The quest to get closer has created states of matter that don't exist anywhere else. Bose-Einstein condensates, superfluids, superconductors. These aren't just scientific curiosities. They're proof that as you move closer to this limit, reality begins to peel back its layers and show you what's been hiding underneath all along. And the technology we have built in this chase has reshaped the world. We've created laboratories where lasers and magnetic traps can chill atoms until they are slower than anything that naturally exists in the universe. We've cooled matter to temperatures colder than the empty vacuum of deep space. And in those places, we've learned how quantum mechanics truly behaves when heat no longer overwhelms it. But this unreachable horizon, this absolute zero, isn't just a frustration, it's also a gift, because it sets the boundary that defines everything else. Without it, temperature would have no meaning, heat would have no bottom, only a direction we couldn't measure. Absolute zero is the anchor, the limit that keeps the scale of energy grounded. Even if we can never touch it, its presence shapes everything above it. And in a way, there's something comforting about that. Because it means there will always be one more step we can take downward, always another fraction of a degree to reach, always another discovery waiting in that vanishing space between the world we know and the horizon we can't cross. And maybe that's the real point, not to arrive, but to keep getting closer, to keep stripping away the noise until the universe shows us what it looks like when it's as quiet as it can possibly be. Because while we may never truly reach absolute zero, every step toward it teaches us something profound, not just about cold or energy or quantum mechanics, but about the way the universe protects its deepest secrets, offering them up one fraction of a degree at a time. But now that we understand why this limit can never be broken, we can turn to the next question. What exactly is enforcing it? What law holds that boundary in place and keeps absolute zero forever out of reach? This is where we meet the law that draws the line in the cold. We've been following temperature as it drains away, watching motion slow and energy fade. But if you want to know why absolute zero always remains just out of reach, this is where it happens. It's not luck. It's not a flaw in our machines. It's the third law of thermodynamics, nature's unbreakable rule. The third law doesn't shout the way the other laws do. The first law tells you energy can't be created or destroyed. The second law gives you entropy, that unstoppable drift toward disorder. But the third law is quieter. It simply tells you that as a system approaches absolute zero, the amount of work needed to cool it the rest of the way grows without limit, It doesn't matter how clever you are or what technology you invent. Nature will always add one more wall between you and that last degree. This isn't just theory. You can see it in every experiment. The first steps downward from room temperature are easy. Cool something with ice, with liquid nitrogen, with liquid helium, and the temperature drops quickly. But as you keep going, each fraction of a degree takes more and more effort. It's like draining a glass of water only to find that no matter how much you pour out, there's always a thin film left clinging to the sides, refusing to leave. That final trace of energy is stubborn. This happens because of entropy. Near absolute zero, a system's entropy, its disorder, approaches a minimum. All the particles settle into their lowest energy states, and there's nowhere left for them to go. The random jostling that normally lets energy spread out simply stops happening. And if there's no randomness left to drain, there's nothing left to remove. You can push the system closer and closer to that perfect order, but you'll never erase that last sliver of motion entirely. And here's where quantum mechanics steps in, making the third law even more absolute. Even in this deep freeze, there's zero-point energy, the unavoidable hum of the quantum world. It's what keeps atoms from being perfectly still. No matter how powerful your cooling methods, you can't take that hum away because it isn't heat. It's not something you can remove. It's a built-in feature of reality itself. This is why scientists describe absolute zero as a limit, not a destination. You can get closer than you ever thought possible, 1/1000th of a degree above it, even closer than the coldest corners of deep space. But you will never touch it. The law won't bend. And yet, the impossibility of reaching absolute zero is what has driven some of the greatest achievements in physics. Cryogenic labs all over the world have turned this limit into a challenge. They use lasers that nudge atoms to a crawl, magnetic traps that hold them still, and even evaporative cooling, where faster-moving atoms are allowed to escape, leaving the slower ones behind. Each method chips away at motion, pushing matter closer and closer to that boundary, and each time we get nearer, the universe shows us something new. Without the third law, we would never have discovered superconductivity, that perfect flow of electricity without resistance. We would never have seen Bose-Einstein condensates, where matter stops behaving like a cloud of individuals and starts behaving like one seamless entity. We wouldn't have learned that friction can vanish, that entropy can stall, and that time itself seems to blur when motion almost disappears. But this law also says something profound about the universe itself. It tells us that there are limits we can approach, but never cross. It tells us that perfection, in this case the perfect stillness of absolute zero, exists only as a boundary, not a destination. The universe allows you to move closer and closer, but it always keeps one last step beyond reach, as if reminding you that there's always something left to chase, and maybe that's the most beautiful part of it. The third law doesn't just stop us, it shapes the way we explore. It forces us to look at what happens in that narrowing space between what is possible and what is forbidden. It's in that thin, frozen gap that we've made our greatest discoveries, and if this is the limit the third law sets, then the next step is clear. We need to see what happens in that space just above the impossible, because this is where matter stops behaving like matter at all. Now we're stepping into the part of the cold where the familiar rules of the universe start to warp. We've seen how the third law of thermodynamics builds an unbreakable wall around absolute zero, but even just above that wall, physics no longer behaves the way it does in the world we know. Here, near the bottom of the thermometer, matter stops following the logic of everyday experience. It begins to twist, stretch, and bend into forms that feel almost impossible, and yet every bit of it is real. At room temperature, physics is comforting. Objects have clear boundaries. Heat moves predictably from one place to another. Particles bounce and collide like tiny billiard balls. But as you cool things down, you strip away that ordinary behavior layer by layer until nothing familiar is left. This is where the quantum world takes over completely, and what you find there is a catalogue of phenomena that exist nowhere else. One of the strangest is superconductivity. At higher temperatures, electrical resistance is everywhere. When you run current through a wire, electrons scatter against the atoms inside it, wasting energy as heat. But as you lower the temperature, that scattering fades. Cool a material enough, and at a certain point something extraordinary happens. Its resistance doesn't just decrease, it vanishes. Electrons begin to pair up and move together in perfect synchrony, gliding through the material without ever colliding, without losing energy, without stopping. They flow forever, as if friction itself has been erased from the universe. Then there are superfluids, those eerie substances that appear when certain liquids, like helium, are chilled to a fraction of a degree above absolute zero. In this state, the liquid stops behaving like a normal fluid. It flows without viscosity, sliding effortlessly through narrow channels and around obstacles without slowing down. It can even creep up the sides of its container and spill over the edges, not because of gravity or pressure, but because in this bizarre world near absolute zero, the usual rules that keep liquids in their place no longer apply. And if that isn't strange enough, this is also where we find Bose-Einstein condensates, those ghostly clouds of atoms that merge into a single quantum state. In this condition, matter behaves as if individuality no longer exists. Millions of atoms collapse into perfect harmony, acting like one vast unified particle. In this frozen domain, the difference between many and one stops mattering. But these phenomena are just the beginning. The deeper you explore this frozen frontier, the more exotic it gets. Quantum tunneling, the phenomenon where particles slip through barriers they should never be able to cross, becomes increasingly significant. It's not a rare exception anymore. It's a dominant way the world behaves. Particles stop caring about boundaries. They move in ways that defy every instinct we've built from living in a warm, noisy universe. Even time itself starts to feel strange here. At these temperatures, the slowing of motion and the reduction of entropy create an environment where events no longer unfold at the same pace we're used to. Processes that would normally happen instantly, chemical reactions, particle interactions, are drawn out, slowed, until they almost appear to hold their breath. The universe down here is not gone, but it is suspended, like a single quiet frame stretched across a canvas of stillness. What's remarkable is that we've actually learned how to reach this frozen edge of physics in the laboratory. Scientists have cooled atoms to billionths of a degree above absolute zero, trapping them with lasers and magnetic fields, and in that deep freeze, they've seen the laws of nature flex in ways that textbooks once only imagined. They've turned ordinary gases into quantum clouds, watched fluids lose their friction, and made electrons flow endlessly, never tiring, never slowing down. This bending of physics near absolute zero isn't just a curiosity, it's a window. It shows us what the universe looks like when the usual layers are stripped away. It's a glimpse at reality without the noise of heat and motion, pure, undistorted behaviour governed only by the most fundamental laws. But perhaps the most extraordinary thing about this realm is what it implies. If the universe can bend this way in the cold, if matter and energy can transform so completely, what else might be hiding down here? What other rules might emerge when we push closer to the ultimate limit? We're entering one of the strangest, most mesmerizing regions of the cold, where matter stops behaving like anything you've ever seen before. This is where superfluids live, those impossible liquids that flow without friction, climb walls, and move forever without losing an ounce of energy. They're not just a scientific curiosity. They are proof that the universe has hidden rules that only reveal themselves when you press reality down toward the bottom of the thermometer. At first glance, a superfluid doesn't look like anything extraordinary. Take liquid helium, for example. Chill it down to just a few degrees above absolute zero, and it behaves like any other liquid. It sloshes around in its container. It has thickness and drag. But if you cool it further, right to the edge of that frozen frontier, everything changes. At a certain temperature, close enough to absolute zero that heat has been nearly erased, helium undergoes a sudden transformation. It stops acting like a liquid, Its viscosity, the property that makes every fluid resist motion just a little, vanishes completely. The helium becomes a superfluid, and from that point on, it moves in ways that seem to defy reason. You can pour it into a container, and it won't just sit there. It will creep up the walls and spill over the edge as if gravity has lost its authority. You can stir it, and it will spin forever because there's nothing left to slow it down. No friction, no resistance, no loss. It's as if the very concept of stopping has been erased from the liquid's vocabulary. And the explanation for this strange behaviour is not hidden in the macroscopic world of ordinary liquids. It's buried deep in quantum mechanics. At these temperatures, the helium atoms lose their individuality. They overlap and lock together into a single unified quantum state, just like in a Bose-Einstein condensate. Instead of moving independently, they move collectively. The whole liquid flows as if it were one single entity. And because of this perfect quantum alignment, there is no scattering, no internal friction, nothing to dissipate its motion. The result is a liquid that can flow endlessly, not because it has no energy loss, but because, at this scale, there is no mechanism left to create that loss in the first place. This frictionless flow isn't just an odd laboratory trick. It changes how we see the fabric of matter itself. It shows us that in the deep cold, the universe is capable of sustaining states of perfect efficiency, states that make our ordinary world of resistance and waste look crude by comparison. And it doesn't stop with helium. The same principle that creates superfluids also helps explain superconductors, materials that carry electric current forever without resistance. Different systems, same rule. Near absolute zero, motion stops being messy. It becomes perfect. And there's something strangely hypnotic about that idea. We live in a universe defined by loss. Push a swing, and it slows down. Roll a ball, and it stops. Run electricity through a wire, and heat bleeds away. But down here, in the silence near absolute zero, those rules are suspended. Push a superfluid, and it never slows. Create a current in a superconductor, and it will circle endlessly. In this frozen domain, perfection isn't just theoretical, it's real. But there's a deeper implication hiding in this. If friction can disappear in these conditions, if matter can move endlessly without wasting energy, then what does that say about the limits of the physical world? Does this mean that the universe, in its most stripped-down form, has no natural reason to decay? Is friction not a fundamental feature of nature, but only a symptom of heat and chaos? When you strip all of that away, you find a level of order that feels almost alien. And yet, this alien order isn't out of reach. We've touched it in the laboratory. We've created superfluids and watched them climb up the sides of their containers, behaving like no ordinary liquid should. We've built superconducting circuits that could, in theory, carry current for longer than the universe itself has existed. These are not just experiments. They are glimpses into what matter looks like when it sheds the limitations of our warm, disorderly world. But the closer we get to this perfection, the more it feels like we're peeling back a layer of the universe that was never meant to be visible. Superfluids and superconductors aren't just oddities. They are reminders that beneath the noise of heat, the universe hides a kind of flawless rhythm, a state where things no longer resist or decay. And if that's what lives here, at the edge of the cold, then we have to wonder, what else might be hiding just a fraction of a degree further down? What happens if we follow this descent until we reach the faintest hum of motion left in the universe? While we've been following absolute zero downward in the laboratory, the universe has been holding its own frozen secrets in the vast dark between the stars. Space, for all its emptiness, is not truly empty. It has a temperature, and that temperature, just a few degrees above absolute zero, is the quiet backdrop against which everything else exists. It's the cosmic floor, the coldest natural stage in all of reality, and if we want to understand what absolute zero really means, this is where we need to look. When you step out of the warmth of planets, away from stars and into the deep interstellar void, you find yourself surrounded by a darkness so complete it feels almost physical. There is no sunlight here, no warmth bleeding from familiar worlds, only the dim afterglow of the Big Bang itself, stretched thin over billions of years until it has cooled to just 2.7 Kelvin. That's only a few degrees above absolute zero. It's called the cosmic microwave background, a faint, ever-present sea of radiation, left behind from the moment the universe was born. It has been fading for nearly 14 billion years, and now it's the quiet temperature that fills the universe from one edge to the other. This means that if you were to float out there, far from every star, you'd be surrounded by a cold so deep it would make any winter on Earth seem like fire. And yet, even this is not truly absolute zero. Space itself, in all its emptiness, is still a little too warm to be perfectly still. That lingering microwave glow, those tiny photons left over from the dawn of time, keep the universe from reaching the bottom of the scale. Even in the farthest, darkest corners of the cosmos, there is still motion. There is still energy. But there are places out there that come close. Near the shadowed edges of interstellar clouds, where dust and gas gather in lightless knots, temperatures drop to just a fraction of a degree above absolute zero. These are some of the coldest natural regions in existence, cosmic laboratories where matter slows to an almost perfect hush. Here, molecules move so slowly that they can stick together in delicate clusters, building the first pieces of new stars and planets in the quiet. It's a kind of frozen womb for creation, where the absence of heat becomes a space for building. And then there are the even stranger places. Around neutron stars and black holes, gravity bends everything, including light, including time itself. In the deep shadow of these collapsed giants, there are regions so empty of energy that their temperature dips nearly to nothing. And yet, even there, absolute zero refuses to appear. Quantum mechanics won't allow it. 0-point energy, the faint hum built into the universe itself, keeps everything from ever truly stopping. It's as if reality has a rule that says nothing. Not even the coldest corners of space can be perfectly still. This is what makes absolute zero such a haunting idea. It's not just an unattainable number on a scale, it's a boundary that exists everywhere, even in the emptiest reaches of the cosmos. No matter how far you go from the stars, no matter how deep into the black you drift, you'll never touch it. You'll only brush against it, feeling it in the silence of those last degrees where matter almost forgets how to move. And yet, those places, those nearly frozen regions of space, are not lifeless. They are not meaningless. They are where the universe slows down enough for us to glimpse what it's made of. They are where astronomers look when they want to study the chemistry of the early cosmos, because only there, in that deep, frozen dark, can fragile molecules survive long enough to tell their story. In a strange way, these places are a bridge between what the universe was and what it's becoming. But perhaps the most fascinating thing about this cosmic cold is what it implies about the future. Because if the universe keeps expanding, keeps cooling, keeps spreading its energy thinner and thinner, then one day, billions upon billions of years from now, all of space will sink closer and closer to absolute zero. Stars will burn out, galaxies will dim, and heat, the restless motion of everything, will fade until the entire cosmos is nothing but a thin, cold whisper of what it once was. And if that happens, we will see what absolute zero looks like, not in a laboratory, not in a single droplet of helium or a trapped cloud of atoms, but across everything. A universe frozen to the edge of stillness, a horizon of cold without end. Let's come back from the silent emptiness of space and step into a place that's almost as strange, our own laboratories here on Earth, where scientists have learned how to push matter closer to absolute zero than anywhere else in the known universe. These are not just rooms filled with equipment. They are modern-day cathedrals of precision, built to strip away motion one fraction of a degree at a time, until the ordinary world disappears and the hidden rules of reality start to show themselves. When you walk into one of these laboratories, you won't see frost coating the walls or clouds of frozen air swirling around. Absolute cold doesn't look like the movies. What you'll find instead are chambers of polished metal, vacuum pumps humming quietly, lasers so precise they can push on individual atoms, and magnetic traps that hold matter in place as if gravity itself had been rewritten. These are the tools of the coldest science on Earth. The process begins by removing heat in the simplest way imaginable, by isolating a system from everything around it. First, scientists pull almost all the air out of a chamber, creating a vacuum so empty it makes outer space look crowded. Without air, there are no collisions to warm the experiment. Then they use liquid nitrogen at 77 Kelvin and liquid helium at 4 Kelvin to draw the temperature down further. This is where most everyday intuition about cold ends, but for these labs it's only the beginning. From there, the descent slows, because each step closer to absolute zero becomes exponentially harder. Lasers are used next, not to heat, but to cool. By tuning a laser to just the right frequency, scientists can actually nudge atoms in the opposite direction of their motion, slowing them down like invisible hands pressing gently against each particle's movement. This laser cooling technique has brought atoms to temperatures within billionths of a degree of absolute zero, a place so cold it doesn't exist anywhere naturally, not even in the deepest interstellar void. But it doesn't stop there. Once the atoms are slowed, magnetic and optical traps hold them in place, preventing even the smallest stray vibrations from warming them again. And then, through a process called evaporative cooling, scientists let the hottest atoms escape, leaving only the coldest, slowest ones behind. With every step, the remaining atoms grow quieter, calmer, and more synchronized until finally, what's left is no longer just matter as we know it. It's something new. This is how Bose-Einstein condensates are born. It's how we've created superfluids in controlled settings, watched superconductivity unfold in real time, and studied quantum mechanics on a scale big enough to see. These laboratories are the closest thing we've ever built to a window into another version of the universe, one where heat, motion, and even time seem to loosen their grip. But this isn't just about pure curiosity. These experiments have reshaped technology. MRI machines, quantum computers, ultra-precise atomic clocks, and the superconducting circuits used in cutting-edge research. All of them owe their existence to the work done in these cold laboratories. By chasing the lowest temperatures, scientists haven't just revealed the foundations of reality. They've started building tools that rely on those foundations, and yet no matter how far they push, the third law of thermodynamics still stands in the way. Absolute zero remains unreachable, a horizon that mocks every achievement. But here's the thing. Every time scientists take one more step toward it, even by the tiniest fraction of a degree, the universe answers with something new. A new state of matter, a new quantum effect, a new glimpse of how reality behaves when you take away almost everything except its barest essentials. If you were to stand in one of these labs and look at a cloud of atoms cooled to nearly absolute zero, you'd see something that feels almost impossible. A ghostly shimmering cloud suspended in magnetic fields, sitting at a temperature where motion has nearly stopped, but not entirely. The atoms blur into one another, becoming less like individual particles and more like pieces of a single quiet wave. It's not just cold, it's a kind of stillness that feels alive in its own strange way. Let's step even further down, into the deep quiet near absolute zero, where one of the strangest and most counterintuitive behaviours of the universe begins to dominate. quantum tunneling. This is where particles stop caring about boundaries, where walls no longer mean stop, and where matter reveals a side of itself that feels less like physics and more like a magic trick written into the laws of nature. In our warm, everyday world, boundaries are simple. If you throw a ball at a wall, it bounces back. If you don't have enough energy to climb over a hill, you stay put. This is the kind of logic we live by, but at the quantum level, things don't work that way. Down here, particles don't behave like little billiard balls. They act like waves, and waves can do something that particles, at least by classical rules, should never be able to do. They can spread, they can stretch, and sometimes they can slip through barriers as if the barriers weren't there at all. This is quantum tunneling. It doesn't matter if a particle doesn't have enough energy to cross a barrier in the usual way. There's always a tiny chance, thanks to the strange rules of quantum mechanics, that it will simply appear on the other side. Most of the time, this chance is vanishingly small. In our warm, noisy world, where particles are bouncing around chaotically, these quantum effects are buried beneath a storm of random motion. But in the frozen stillness near absolute zero, where nearly all thermal motion has been stripped away, those tiny probabilities no longer hide. They stand out. At these temperatures, particles are no longer distracted by heat. They settle into their lowest possible energy states, and their quantum nature comes into focus. Their wave-like behavior dominates. Instead of behaving like individual little marbles, they smear out into probability clouds. And when those clouds brush up against a barrier, a piece of them leaks through. Not metaphorically, literally. That's tunneling. In laboratories cooled to billionths of a degree above absolute zero, scientists have watched this happen. They've trapped atoms in ultra-cold lattices, tiny grids of light, and seen them do something impossible. Instead of sitting locked in place, some of them simply vanish from one spot and reappear in another, without crossing the space between in any way we would recognize. It's not that the atoms are ignoring the rules, it's that we've peeled back enough layers of temperature to see the rules that were there all along. And tunneling isn't just a curiosity, it's the key to much of the universe's hidden machinery. The fusion reactions that power the sun, they depend on tunneling. Protons in the heart of a star don't have enough energy to collide and fuse under normal circumstances. But quantum tunneling gives them a way to cheat, slipping through barriers they couldn't otherwise cross. Without tunneling, the stars would never burn. Without tunneling, the universe as we know it wouldn't exist. But in the frozen world near absolute zero, tunneling takes on an even more direct role. In superconductors, for example, pairs of electrons, called Cooper pairs, can tunnel through barriers effortlessly, creating currents that flow forever without losing energy. In quantum computing experiments, scientists rely on tunneling to manipulate particles in ways that classical physics would call impossible. At this temperature scale, tunneling isn't just an occasional oddity, it's the main event. What makes all of this so haunting is how it reshapes our sense of what's real. At ordinary temperatures, we can pretend that the world is solid and definite. Things stay where they are. Barriers hold. Time flows. But in the frozen quiet at the edge of absolute zero, the world loosens its grip on that comforting solidity. Particles move in ways you can't point to or watch. They simply exist in more than one place at once, and sometimes they decide to emerge where you least expect them. And the deeper you follow this descent, the more it feels like you're stepping out of the world we know and into one that was always running underneath it, hidden by the noise of heat and motion. Here, near absolute zero, that noise is gone. The whispers of the quantum world are no longer whispers. They are the only sound left. If tunneling shows us how matter behaves when the cold strips away the ordinary, then the next question is even stranger. What about life itself? What would happen if something living could touch this edge of frozen reality, where motion slows, energy fades, and the rules we know give way entirely? We've seen what happens to atoms. We've watched matter lose its individuality, slip into quantum states, and tunnel through barriers as if the rules of the ordinary world no longer apply. But now comes the stranger question. What if life, our kind of life, built from warmth and motion, could ever touch this place? What if we could bring biology to the edge of absolute zero, where motion stops and the universe holds its breath? Life, as we know it, is built on motion. Every cell in your body, every spark of thought in your brain, every chemical reaction that fuels existence, none of it works without energy. Heat is part of the story of being alive. Proteins fold, enzymes work, molecules bump into each other in the constant, restless dance that keeps living systems running. Even at rest, even in sleep, life is never still. It hums with motion. It depends on it. Now imagine taking all of that and lowering it. Not just by a little, not to the cold of a winter night or the chill of liquid nitrogen, but down, far down, toward the silent edge near absolute zero. As the temperature falls, motion slows. The biochemical reactions that make thought and memory and heartbeat possible begin to lag. Below a certain point, they stop. The machinery of life is not built for this kind of stillness. For us, the descent to absolute zero isn't just cold. It's the end of activity itself. And yet, here's the strange part. There's a way in which this is already true. In cryogenic science, researchers freeze biological material close to these extremes. Not living people or animals, but cells, embryos, even entire organs, to preserve them. By lowering their temperature far enough, they slow every process inside them until nothing changes, nothing decays. It's not life as we usually define it. It's something in between, paused, suspended in a kind of artificial stillness that can last for years, even decades. This is not absolute zero, of course. It's nowhere near it. But it brushes against the same principle. The colder you get, the slower the clock of biology ticks. In theory, if you could keep cooling further and further without damaging the structures of life, you'd approach a kind of perfect stasis. No aging, no decay, no movement forward in time, at least not in the way we experience it now. But what happens if you push it even further? If you could bring a living system down to the edge of absolute zero, without breaking it, would it still be alive? Or would it become something else entirely? Would it simply be frozen matter, indistinguishable from the atoms around it, waiting for heat to return? Or would it exist in some strange quantum limbo suspended in the same ghostly quiet where even time itself seems to lose its urgency? There are experiments that hint at this boundary. Physicists have cooled single atoms, single molecules, even clusters of particles to near absolute zero conditions, and seen them fall into perfect quantum coherence, behaving as one unified wave. Life, however, is not a single particle. It's a system, a vast, tangled network of processes, all of which depend on movement. And if you drain away that movement entirely, you don't simply pause life. You erase the difference between living and non-living. And maybe that's why this question feels so heavy. Absolute zero isn't just a number. It's the place where the dividing line between alive and inert blurs into something meaningless. It's a reminder that everything living is just organized motion, and if you strip the motion away, you're left with the same quiet matter as everything else. But there's another side to this too, one that's harder to ignore. If life could survive this kind of stillness, if, somehow, there were a way to reach this deep frozen edge and hold ourselves there, it would be like stepping out of time. No aging, no change, no end. In the coldest imaginable state, you wouldn't be dead, but you wouldn't be alive in any way we recognize either. You'd simply wait, perfectly preserved, in a universe where nothing moves. And maybe that's the closest we'll ever come to touching eternity. Not in fire, not in chaos, but in a silence so deep that even time forgets how to move forward. But before we can follow that thought too far, there's something else waiting in this frozen descent. Because if life can't quite reach this place, there's one thing that can: the particles themselves. And when they get this quiet, they don't just slow down, they become something so silent it almost feels supernatural. Now we're moving into a place where even the faintest trace of motion fades into something almost imperceptible. We've been talking about atoms slowing down, about heat draining away, about matter transforming into ghostly quantum states. But if we descend further, we reach the quietest point imaginable, the silence of particles, a place where movement no longer feels like movement, where time stretches so thin it almost disappears, and the universe itself seems to hold its breath. In the world we know, nothing is ever still. Even a rock sitting in your hand is buzzing with activity at the microscopic level. Its atoms vibrate, its electrons spin and shift. Every particle hums with the quiet background music of temperature. But at the edge of absolute zero, that music nearly stops. Every vibration slows, every collision fades, and what's left is a kind of order that feels alien, matter reduced to the simplest, most motionless version of itself. But here's the thing, the silence is never perfect. No matter how much you cool a system, you can't strip it entirely of energy. 0-point energy remains. That faint hum of quantum mechanics is always there, a reminder that even in the coldest, stillest place imaginable, the universe can never be entirely quiet. But compared to the restless, chaotic world we live in, this hum is different. It's not the noise of disorder, it's the sound of the universe at its lowest register, the bare minimum motion that reality will allow. When you look at matter in this state, you see the world stripped down to its foundation. Particles aren't bouncing wildly or colliding randomly. They're synchronized, their behavior dictated by quantum mechanics alone. It's the silence of a system that has been drained of almost everything except its most fundamental laws. And in that silence, matter begins to reveal things that we can't see anywhere else. This is where the lines between particles blur. This is where Bose-Einstein condensates form, not as an exception, but as the natural state of things. Millions of atoms, once separate, once noisy, collapse into one single quantum identity. The usual individuality of matter, its tendency to break apart into countless tiny pieces, is replaced by an eerie unity. It's no longer a crowd of atoms, it's a single, quiet entity. And in this state, strange things happen. Fluids that would normally resist motion lose all friction. Electrons stop scattering and begin to flow forever. Barriers that should block particles become irrelevant as tunneling dominates. It's a world where the laws of motion feel rewritten, not because they've changed, but because we've finally pushed past the layers of heat and randomness that were hiding what was always there. And then there's time. Because if movement slows, if collisions fade, if entropy nearly vanishes, time begins to feel different. It's not gone, but it's stretched, thinned out to the point where the distinction between one moment and the next starts to dissolve. Down here, in the silence of particles, time doesn't rush forward like a river. It lingers, it hovers. It feels less like a flow and more like a still, deep pool. This is why the silence of particles matters. It isn't just an extreme condition. It's a way of seeing the universe without the noise of everything else layered on top. When scientists create these states in their laboratories, they're not just cooling atoms for the sake of it. They're peeling the world back to its most fundamental state, the skeleton of reality, exposed by the absence of motion. And this silence isn't empty. It's full of information. It's where quantum mechanics speaks the loudest, where the smallest, strangest rules of the universe stop being background details and start defining everything. It's where we learn what matter really is, what energy really means, and what's left when you take everything else away. If this is what happens when particles fall quiet, the next question is even deeper. What is temperature really? And what does it mean to speak of cold and heat at all, if at the bottom of the scale, silence and motion blend into something that no longer feels like either one? It's time to pause and ask a question that has been quietly sitting underneath everything we've been talking about. We've spoken of cold and heat, of motion and stillness, of particles slowing until they nearly stop. But what does temperature really mean? What is it that we're measuring when we talk about degrees, about Kelvin, about how close something is to absolute zero? And why does this idea, which seems so simple on the surface, lead us straight to the foundations of the universe itself? Temperature, at its core, isn't about numbers on a thermometer. It isn't even about how something feels when you touch it. Temperature is motion. Not motion in the way we see it every day, like a car rolling down a street or a planet orbiting a star, but microscopic motion. The invisible dance of atoms and molecules bumping into each other, vibrating, colliding, and constantly exchanging energy. When something is warm, it simply means those particles are moving quickly, crashing into one another with more force and frequency. When something is cold, their motion slows. That's it. No mystery, just motion. And yet, if you follow that motion downward, if you take it away piece by piece, you eventually reach a strange boundary, a place where the particles can't slow down any further because there is no more motion left to remove. That's absolute zero. The point where temperature is no longer about speed or energy because there's nothing left to give. This is why absolute zero has always been such a profound idea. It's not just about cold, it's about the very bottom of motion itself. And when you understand that, you start to see why temperature connects to everything, from the behavior of stars to the way time flows to the strange, quiet quantum effects that only appear in the frozen dark. But here's where it gets even more fascinating. Temperature isn't just about individual particles moving around. It's about how those particles share energy. In a hot object, energy is spread out chaotically. Molecules collide at random, constantly trading speed and direction. That chaos is what creates heat. But as you cool something down, the collisions slow, the exchanges become less frequent, and order begins to creep in. And when you get close enough to absolute zero, that order becomes overwhelming. Instead of countless particles each moving in their own way, you start to see the emergence of collective behavior, particles acting together as if they are parts of one larger thing. That's what happens in Bose-Einstein condensates, in superconductors, in superfluids. Temperature isn't just a measure of how fast anymore. It becomes a threshold for transformation, a marker of when ordinary matter gives way to something entirely different. And this isn't just an abstract concept. When scientists cool something to billionths of a degree above absolute zero, they're not just making it colder, they're creating a new environment where the usual rules collapse. In that world, temperature stops feeling like a simple scale and starts to look more like a key, one that unlocks phenomena that are invisible at any other point on the thermometer. Even more strangely, temperature is tied directly to entropy, that measure of disorder we talked about before. As temperature drops, entropy falls with it. At absolute zero, entropy reaches its minimum because there is no motion left to create disorder. The system isn't just cold, it's almost perfectly ordered, stripped of every unnecessary detail. That's why scientists see these bizarre quantum effects down here, because all the noise is gone and the raw skeleton of reality is left behind. But there's one more layer to this. Temperature isn't only a property of matter, it's also a property of information. Physicists studying black holes, for example, have discovered that even these collapsed objects, places where matter is crushed out of existence, can be described in terms of temperature and entropy. In other words, the same idea that tells you how warm your coffee is also describes the deep physics of the universe's most extreme objects. And maybe that's the point. Temperature isn't just about cold or heat, it's a language, a way of describing how energy moves, how matter behaves, and how order and disorder shape the world. When we talk about absolute zero, we're not just talking about a number. We're talking about the floor beneath that language, the ultimate stillness against which all motion is measured. But if that's true, if temperature is really about motion, energy and information, then what happens when the universe itself keeps cooling? What happens if one day, everything, every star, every planet, every particle, falls toward that silent floor? Because next, we're going to step away from the laboratory, away from the microscopic world of atoms, and look at the universe itself, its far future, its last horizon, and ask, could everything one day sink into absolute zero? Could the entire universe one day end in absolute zero? Could everything, all the stars, all the motion, all the energy fade until there's nothing left but a silent, frozen cosmos resting at the bottom of the thermometer forever? To understand this, we need to look not at where the universe is now, but at where it's heading. Right now, the universe is expanding. Space itself is stretching, carrying galaxies farther and farther apart. And as it does, the leftover heat from the Big Bang, the faint cosmic glow we call the cosmic microwave background, is cooling. Billions of years ago, that glow was scorching. Today, it's just 2.7 Kelvin, only a few degrees above absolute zero. And if this expansion keeps going, it will keep cooling. Over unimaginable stretches of time, the stars will burn out. The bright blazing suns that fill our night sky will exhaust their fuel one by one. The small ones will fade into dim embers. The large ones will collapse, explode, or leave behind black holes. And once those black holes finish devouring what they can, even they will slowly evaporate through a process called Hawking radiation, shrinking away into nothing. What happens then? You're left with a universe that is almost entirely dark. No stars, no galaxies bright enough to see. Just a thin mist of particles scattered across space. And those particles too will keep cooling. Every interaction between them will become slower, every transfer of energy weaker, until almost nothing happens at all. This is what physicists call the heat death of the universe, but it's a misleading name because it isn't hot. It's the opposite. It's a future of freezing emptiness, where all usable energy has been spent and there is no more work left to do. It's a universe drifting downward toward absolute zero, not in one place, not in one experiment, but everywhere, all at once. But here's the strange part. Even then, it will never quite get there. Just as in the lab, where the third law of thermodynamics holds the line, the universe itself will obey that same rule. Absolute zero will always remain just out of reach. Particles will retain their zero-point energy, that faint hum of quantum motion that can never fully be erased. There will be no heat, no life, no movement in any familiar sense, but there will still be that last whisper of existence, a quiet vibration at the foundation of reality. And in that frozen future, time will become something almost unrecognizable. Without stars, without heat, without entropy increasing in any meaningful way, time will stop feeling like a river. It will flatten out into a kind of endless stillness, where nothing changes because nothing is left to change. The universe won't end with a bang or a collapse. It will end with a kind of perfect, inescapable quiet. This vision isn't the only possible ending for the cosmos, but it's the one that follows naturally from what we know now. The same laws of thermodynamics that keep absolute zero out of reach in our laboratories also stretch their influence across the entire universe. They tell us that everything is slowly running down, losing energy, becoming simpler, colder, and quieter with each passing epoch. And in that sense, absolute zero is not just a number on a thermometer, it's the destination written into the fabric of reality itself. Not because we'll ever reach it, but because everything is falling toward it, one slow step at a time. Yet even in that bleak stillness, there's something oddly comforting. The same rules that make the universe burn with stars also ensure that, in the very end, it will rest, not in fire, not in violence, but in silence. But before we settle into that far-off picture of eternity, there's one last thing we need to understand. If the universe is always sliding toward this frozen horizon, what happens to the laws of physics themselves when they're pushed that far? Could they change? Could new rules emerge, hidden in the deep cold, waiting for the end to reveal them? If the universe really does keep cooling forever, if everything we see is fated to slide closer and closer to absolute zero, then the question isn't just about what freezes. It's about what happens to reality itself in a cosmos where almost nothing moves. We've already seen how near absolute zero conditions in laboratories change the rules. Atoms stop acting like individuals, matter collapses into quantum states, friction vanishes, and electricity flows forever without resistance. These are not just oddities, they are hints. They tell us that in the deep cold, the familiar version of physics is only a thin surface layer. Beneath it is something older, stranger, and far less concerned with the boundaries we use to organise the world. Now imagine applying that not to a tiny lab experiment, but to the entire universe. As the cosmos cools, energy thins out, stars fade, galaxies grow dim, and in that unimaginable future, the universe would be dominated by the physics of the cold, rules that we only glimpse today in brief, controlled bursts in our laboratories. Quantum mechanics, for example, wouldn't just be a set of principles for tiny particles, it would be the language of everything. Without heat to drown it out, quantum effects would no longer be confined to the microscopic. They could stretch across distances, binding matter into coherent states on scales we can't currently imagine. It wouldn't be a world of planets and stars anymore. It would be a world of quantum fields, silent and vast, where the distinction between one thing and many things might simply stop mattering. And what about time? If the arrow of time is tied to entropy, then in a universe this cold, where entropy barely changes, time itself might lose its meaning. It wouldn't stop entirely. 0-point energy would still hum softly in the background, giving the universe just enough motion to keep existing. But time would no longer feel like a flow. It would be something else, static, flat, almost unnoticeable, as though the universe had reached a state where nothing was left to mark its passing. Some physicists even speculate that at these scales new laws could emerge. There may be forms of matter or states of energy that only exist in the deep cold, exotic particles that can't survive in the noisy hot conditions of the young universe might become stable. Quantum fields might lock together in strange, ordered patterns, creating structures not bound by the same rules that govern galaxies and stars today. And then there's the question of information. In this frozen cosmos, where change slows to an almost perfect stop, the information written into the fabric of the universe might no longer scatter and decay. It might settle into a final, unchanging pattern, a record of everything that ever happened, suspended in a universe that has nothing left to do but keep existing. This is why the deep cold isn't just an ending, it's also a kind of unveiling. Heat hides the true foundations of reality, motion covers up the stillness underneath. But as the universe cools, those layers are stripped away. What's left might not look anything like the world we know, but it would be built from the same rules, revealed in their purest form, and maybe that's why absolute zero, even if it's unreachable, has always been such a powerful idea. Because it isn't just the absence of heat, it's a threshold. Cross it, or even come close, and you stop seeing the universe the way we've always seen it. You start seeing it the way it is when everything unnecessary has been stripped away. We've followed the cold from the restless motion of atoms to the quiet hum of 0-point energy. We've watched matter dissolve into ghostly states, seen time lose its urgency, and imagined a universe where even stars and galaxies have faded into silence. And now, there's nowhere left to go. no further to descend, only a kind of stillness so deep it feels less like an ending and more like the quiet that has always been waiting underneath everything. This is the stillness of nothing. Not emptiness, not absence, but the baseline of reality itself. Here, at the unreachable edge of absolute zero, there is no heat left to spill, no motion left to slow. Every atom has been pressed into its lowest possible state. Every trace of entropy has been pared down to the faintest whisper. It's not dead, it's not lifeless, it's simply quiet. If you could stand here, not with your body but with your mind, you wouldn't hear anything. You wouldn't see anything moving. Time would stretch until it barely seemed to matter at all. And in that vast, frozen silence, the universe would look different, not because it had changed, but because all the layers of motion and chaos that normally cover it had been stripped away. For the first time, you'd see what was always beneath it all, the calm, unshakable ground on which everything else is built. And strangely, there's something comforting about that. Absolute zero isn't just the bottom of the thermometer, it's a reminder that beneath all the heat and motion, beneath the noise of life and the restlessness of stars, there is a deeper order, a quiet foundation that holds even when everything else burns out. It's not a place we can ever touch, but it's there, anchoring the scale of the universe, defining the boundary between what can move and what can never quite stop. We'll never reach it. The third law of thermodynamics will keep it forever out of reach, the same way the horizon always stays one step ahead when you walk toward it. But maybe that's what makes it beautiful. It means there's always something left to chase, always another fraction of a degree to explore, always one more hidden truth buried in the cold. And when you think about it like that, absolute zero isn't really an ending at all. It's the quiet underneath every beginning. It's the silence that has always been there, waiting behind the scenes, while everything else moves and changes and burns. And even if we never touch it, even if we only ever approach it, it gives shape to everything above it. The warmth of your own body, the fire in the stars, the heat of the first moment of the universe itself. So here we are, at the bottom of the thermometer. No motion left to slow, no heat left to lose. Just the deep, steady hum of reality at its quietest, holding the universe together while it rests. And maybe, if you let yourself settle here for a moment, you can feel a piece of that quiet too. The kind that doesn't rush, the kind that doesn't demand anything, the kind that just is. Thank you for drifting here with me. If you found comfort in this stillness, if this slow walk to the edge of cold has given you a place to breathe, I'd be grateful if you left a like, maybe even subscribed so we can keep exploring the quiet corners of the universe together. Now just rest here for a while, in the calm, in the quiet, in the stillness of nothing, because for now, there's nowhere else we need to go. And now, as we leave this frozen horizon behind, you can feel the quiet lingering, like a weightless blanket stretched across the mind. We've drifted down from the restless heat of motion to the soft hum beneath it all, from atoms that dance to a universe that may one day fall silent. And if there's one thing this journey toward absolute zero shows us, it's that even in the coldest, stillest place imaginable, the universe doesn't stop. It simply rests. So if you're lying there, letting this calm settle in, take a moment and let it stay with you. The stars will keep burning for now, the world will keep turning, and motion will return. But here, for just a little while, you've been as close as anyone can be to the quiet at the bottom of everything. If this brought you a little peace tonight, if it helped you drift a little closer to that same quiet, I'd be grateful if you gave this video a like or subscribed, so you can join me the next time we wander somewhere strange and beautiful. For now, just rest. Close your eyes and let the sound of the universe's stillness stay with you. Because even in the deepest cold, there's comfort in knowing the silence was always there, waiting.